quiz 2 prep questions. This one's from this exam. And I'm starting to think that maybe this would be a good one for your quiz. So there's a little hint for those of you that are actually paying attention to this study material. Okay, so let's go through the process again. Now this one's not vats of water, it's balloons. But it tells you the two balloons are at the same height at time 0. It's very similar to the last question I just did. Time t is measured in minutes. And I'll finish this with visuals like I did in the last one. But they're giving you the derivative or the rate for balloon A. That's like the speedometer speed. And then they're giving you the height of balloon B. And really the point of these questions is to make sure you're understanding how to analyze a function and what you're given. Okay, so in this first question, they tell us that they start at the same height. So that means you can actually get this. You can say this is just an indirect way to tell us that this is also 30. You can see that right there when you plug in 0. So they're giving you an initial value, and you know the derivative. And the question says to find the formula for A. So this is a direct application of what we've been doing in chapter 12. So here we go. So we say A of t is the integral of 15 minus 5 halves t. You don't even have to write that, but you need to know that you're doing an antiderivative. So 15t minus the power goes up, so it becomes 5 fourths because there's going to be a 1/2 t squared plus c. Then we plug in our initial condition. So our initial condition is that this will come out to be 30 when I plug in 0. So let's do that. So 15 times 0 minus 5 fourths, 0 squared plus c is 30. You should always think this way. Now in this case that happens to tell us c is 30, but it isn't always the case that this number is c. That somebody was messing that up on the discussion board. Okay, so that question is really a quick chapter 12 check-in. Do you know if I give you a derivative that sort of directly follows from our rules, can you find that function? So again, your quiz will have some small chapter 12 thing like this, and you just need to be aware it's coming, and each of these has this. And this is a skill we need for the exam, so there you go. The rest of the questions are going to be about this idea of what's the shape of my graph? How do I analyze my function? That's the big skill. I'm kind of slowing down to make sure we know this, because that's the big skill of I want students leaving my course to be able to analyze a function. So if you go on into other classes, whether it's econ or business, and you encounter a function, you can think about what's going on. What does it look like? When is it increasing? Where is it highest? Where is it lowest? I think that's a general skill we should all know if we're going on into courses that involve functions. Okay. And I also think just the language of this would help you. Okay, so give an interval over which balloon B is concave down. So we're talking about the height of balloon B. So first thing we're going to do is write down the formula for the height of balloon B. So I've been giving this to try to just, hopefully this becomes second nature, but I'm getting a lot of students saying they have trouble reading a question. So let's talk about that. So the original question is the height of balloon B. That's what it's asking about. And then it's asking about when it's concave down. And so I should realize that I need the second derivative of the height of balloon B. And I need to figure out when it's concave down, which is when it's negative. So the very first thing I would write is B of t. Now they give it in the problem, it's up above. Rather than keep scrolling up and back, I have it written here. Minus 5t squared plus 24t plus 30. So we really could immediately start working. It's asking something about the shape of the graph, the shape of the movement, so we want to find the second derivative, t squared minus 10t. First derivative tells me the slope, but the question isn't about the slope. The second derivative tells me how the slope changes, and as we discussed back in chapter 10, we can use that to make various conclusions. So if you want to know why, there's a longer discussion, but the moment you see concave up, concave down, or point of inflection, you set this equal to 0. And what does that give you? That gives you t equals 5 if you solve. You add 10, you divide by 2. Okay, how do we finish this? This is the analysis piece. So we draw a little number line, we put a 5 here, and we ask ourselves, what's going on with the second derivative, this 2t minus 10, before and after 5? Is it positive or is it negative? And you can plug in any number you want. Over here, probably the easiest would be 0, and you would see that it's negative. It's negative 10. That means it's concave down. Ultimately, that means the slope is decreasing, and that's what this tells you. This tells you how the slope changes. But if the slope is decreasing, then that tells you the original function is part of a frown. Okay, similarly, if you're bigger than 5, let's say you plug in a 6 or a 7 or a 10, whatever, you're going to get a positive. It's part of a smile. So what was the question? The question is, when is it concave down? And basically the answer I would accept would be x is less than 5. Now I think the way I had students type in answers, they had to type in an interval. I would accept this if a student just wrote that. But you could also write negative infinity to 5. And since this is a business class and we don't work with negatives very often, I also accepted 0 to 5. So all three of these would be acceptable forms of your answer. I think in my solutions I wrote 0 to 5, but I'm just saying that I would have accepted negative infinity to 5. Okay, that's where it's part of a frown. All right, let's keep going. Part C of the question says, find all times at which balloon B changes from falling to rising. So now you're going to have to think about, what does it mean to be falling or rising? That means it's increasing or decreasing. So right away I know it's going to have to do with the height and its first derivative. Second derivative tells me a concavity. Increasing and decreasing is about the first derivative. So this is talking about balloon B. So I would start with balloon B, the height of balloon B, 1/3 t cubed. You don't have to write it again. I'm just showing you the process for any problem. Write down what the problem is asking about. This one's asking about balloon B rising and falling, or increasing or decreasing. So now I'm going to take its derivative, which we've already done, and find when that's equal to 0. So again, I'm trying to just give you a general approach. For those people that say, I'm just not good at math or whatever, I don't think this is a math skill. I mean, reading overlaps with math, but here's a process, so you're just not stuck guessing. We're asking about when the balloon B is increasing or decreasing, so we're going to take its derivative, set it equal to 0, and solve. Now, I would encourage you to stop. I'm just looking at my notes here. I'd encourage you to stop and solve that. You can either use the quadratic formula or you can factor. If you're curious about the factoring method, you put a t here, you put a t here, because t squared is that. And you try to come up with numbers that multiply together to give you positive 24 and add together to give you negative 10. So you just really just think about factors if you don't know this. So to me, negative 6 times negative 4 jumps out at me because it makes 10. So I was just kind of running through possible factors. And then the conclusion from this is t minus 4 is 0, or t minus 6 is 0. And it doesn't take much longer to do the quadratic formula. So there's these 2 points. So if you do the quadratic formula, it'd be negative b plus or minus square root b squared minus 4ac all over 2a. And you'd calculate those two things and you would get 4 and 6. Again, we've talked about this in class, but you'd calculate what's under the radical, then hit the square root button. That's going to be 100 minus 96, so it's 4, so it's going to be 2. So it's 10 plus 2 over 2, which is 6. 10 minus 2 over 2, which is 4. So that wouldn't take that long. You just have to buckle down and do it. Now, how do we figure out when it's rising or falling? That's the analysis piece again. So that's why I like this question. This is a good one. Just sort of, this is how we analyze functions. So now we're going to put a little tick mark at 4 and 6. And then we're going to ask ourselves about the slope. B prime is the slope. B is the original function. B prime is this thing right here. That's the slope of my function. So I'm going to plug in numbers to it. So like if I plug in a 0, I get a positive 24. So that's a positive. That means the original function is uphill. When I plug in a 5, I get a 5 minus 1 is 1 times a 5 minus 6 is negative 1. That's a negative. It's downhill. If I plug in something bigger than a 6, like a 10, let's say, or a 7, doesn't matter, let's say a 7, you're going to get 3 here from plugging this in. You're going to get positive 1 here, so it's going to be positive. It's uphill. Now, if you want to actually plug in numbers and see what you get, that's fine. The question is asking, now we're going to make conclusions. So step 1 is, what was the function about? It was about balloon B and whether it was increasing or decreasing, so we needed B and its derivative. Step 2 was to solve and translate and do this analysis. Step 3 is to do conclusions, and that was part of this analysis. When does it change from falling to rising? And this is why I really like these arrows, because they make it easier for me to see. It changes from falling to rising at 6. That's the only answer. So I hope you're seeing that the goal here is just to be able to, someone hands me a function and they've left my calculus course. I want them to be able to immediately analyze it, tell everything about it. Okay. Last one. Find the longest and lowest and highest altitude reached by balloon A from 0 to 10. So now we're talking about balloon A. And what I'm really fighting is, I noticed on the last exam that there were students where a question would say something about balloon A and they would grab the formula for B. I'm having trouble understanding that piece, so I really want to emphasize this. You got to read the question. If it's talking about balloon A, you're only going to use balloon A formulas. If it's talking about balloon B, you're only going to use balloon B formulas. I don't mean that as a criticism. It's just something I observed, and I want to remedy that. That's a solvable problem. That doesn't have to do with math. Okay, A of t is 15t. It's talking about the altitude of balloon A, so the height of balloon A. So the very first thing I would write is the altitude, this is from an earlier part, plus 30. I'm just going to grab my notes because there's some numbers I'm going to calculate here in a second. So now the question is highest and lowest over an interval. So highest and lowest on an interval, that should get us thinking global max. And the main thing that distinguishes a global max problem from the other problems, because you do pretty much the same thing, but the main difference is you plug in the endpoints and the critical points to your original function, because you're trying to compare them. And there's no, you don't, just because their function has a bump doesn't mean that that's the highest. It could be at the end. And so the main principle we noticed was that we need to plug in the endpoints and the critical numbers. Okay, so endpoints, we can do those right now if we want. You know, you could say, well, I'm running out of time on the test, so I'm going to get as many points as I can get. So let's plug in 0 and see what the height is. It's 30 feet. We already knew that one. Let's plug in 10 and see what the height is. It's going to be 15 times 10. So a little bit of calculation, but we're trying to see who wins. So I did this. This was 150. And this was 100, so 25 times 125, so 55. Yeah, it was 55. And you don't have, you can do this on your calculator. I just hate reaching for a calculator. As you can see, this is, I feel like a calculator slows me down. Next, I need to know, are there any bumps? So I found the beginning and ending. In your head, you should be thinking at 0, it's 30. At 10, it's 55. But that doesn't tell the whole story. Maybe the graph goes like this. Maybe it goes down and then up. I need to find out if it has any bumps. How do we do that? We take the derivative. This is just, we're really just understanding the many uses of the fact that we can find this derivative. We can find this slope formula. Now we can solve this. 15 equals 5 halves t. Multiply both sides by t. And you get t is 6. So there's only one critical point. There's only one bump. Now we might have already known that, because this is a parabola. So here's a question where you would have had kind of many things pointing you to the answer. Okay, now we need to know the height at 6. So in my head, I'm picturing a parabola now. I know that the parabola starts at 30, it comes up, it comes down, and so we're now getting an even clearer picture that this is 30, this is 55, and this is at 6, and this is 10. So it never hurts to draw a little picture if you're kind of confused. My goal is I've given you enough tools that there's kind of many ways to get to your answer. The main things you need to remember, if it's an overall with a beginning and end, you will have to plug into your original function. Everything else we can answer using our little number line approach. Okay, so let's plug in 6. 15 times 6 minus 546 squared plus 30. And I did this. It's not too bad. If I had to do it in my head because I hate calculators, 45 times, I'm doing this times 3, which is 45, times 2, which is 90. Okay, so that would be 90. This would be 36 divided by 4 is 9. So this would be minus 45. Oh, it's doable. I find a lot of times when a calculation looks bad, if I just pause for a second and do a little bit of it, it's not as bad as we think, and that's what we should be practicing on the homework before we just reach for a calculator, I think. Because in doing so, we'll get better at this. So there you go, no calculator. This was 75, so that's the maximum. 30 was the minimum. So we would say this is the maximum, this is the minimum. So that's a good, I like that exercise overall because it has all the features. We did a first derivative analysis here. We did a second derivative analysis, which we only do if it mentions inflection or concave up or concave down. And we did a global max and min. And you can see two of the questions we took the first derivative and set it equal to 0. One of the questions we took the second derivative and set it equal to 0. My goal here is to get you to start to put these ideas together. We shouldn't think of this as a bunch of different things. Just briefly to wrap up, here's a visual I made. And let's take a look. So here on the left is balloon A. That's that parabola we were just doing. The highest point here is 75. The lowest point here was 30. The graph only went to 10, and 10 was 55. So between 0 and 10, we can see that makes sense. And we didn't actually have to graph it. The graphing takes longer. The other questions were about balloon B. And balloon, we found out when it had a point of inflection, and we found out when it was increasing and decreasing. So let's take a look at that picture. Here's balloon B over here. You can see, sorry, no, I'm grabbing this one. But balloon B went up, it went down a tiny bit, and then it went up a little bit. So balloon B had these two little bumps right there and right there, and then it went up. So it only was decreasing very briefly. In fact, if you were to look at the picture, it doesn't even look like it's decreasing because I haven't zoomed in very much. But there is this moment, and what's happening in the original function, in the derivative, is you can see it's downhill only in that small piece. So it switches from downhill to uphill right there. Okay, what were our questions we asked? When does it switch from downhill to uphill, from falling to rising? That was at 6. We found that. And when was it concave down? It was part of a frown before 5. So let's look at that again. Part of a frown before we got to 5. So there's this point of inflection somewhere in the middle here where it switches from a frown to a smile. That's going to be when the second derivative is 0, which is also where this is lowest. So again, the second derivative just gives you a little more information. For the first function, the second derivative is just negative 2.5. It's always concave down. But for this one, it changes. Concave down to concave up. So we're learning to do all the stuff we see in these pictures, but without the pictures. And it's really fast. I mean, if you actually go back, even with the explanation, I was able to do those problems very quickly. And that's what I want you to be able to do. So that's why we're taking a lot of time on this quiz, to make sure we master this idea. It is very likely that your quiz will be this question. So I'm giving you a lot of hints here. I'm going to change a few numbers, but I want to reward the people who are actually preparing. Okay, hope that's helpful.